Morning, everyone. So we're going to continue our review with Chapter 7 on equilibrium. Again, these notes here are taken from my regular Chem 12 course here. In regular Chem 12, they actually, after they do equilibrium, they do a separate chapter on solubility. For us in IB, we're just going to treat that solubility towards the end, just as an application of some of these equilibrium concepts. We saw this equilibrium concept come back again in our acid-base chapter as well as redox, so sort of the better that we understand this equilibrium, it'll do us good in the long run. So we'll start off with the concept, just defining what is an equilibrium reaction. An equilibrium reaction, first thing that has to happen is your reactions have to be reversible. So although we generally do still put reactants on the left and products on the right, we had that activation barrier from our kinetics chapter here. When we do the forward reaction, energy, and this is reaction, reactants would just be going from left to right. They have to go over this energy hill. So that's the forward direction. Because this is a reaction coordinate, we can imagine our products are the reactants, and they actually reform reactants in going the reverse direction. So there's our symbol for equilibrium. So this double-headed arrow, different from the double-headed arrow for resonance. Resonance was like this, so make sure you do your reversible reactions correctly here. And essentially, equilibrium actually just means forward rate equals reverse rate. The language that we're going to use is equilibrium in chemistry, at least, is dynamic. Let's compare that to the physics case here. In physics, equilibrium is static. So if I have an object that's just sitting there, when it looks like nothing's happening macroscopically, it's because nothing's happening. But in our case here, we might have some saturated solution here, a solid sitting inside the liquid. It doesn't look like anything's happening, so we still have some of these same macroscopic are constant. So outwardly, everything looks the same. And yet, if I have a powerful enough microscope, microscopic things are still happening. And in this case here, the microscopic things are reactions. Just make a note to yourself, your reactions continue. The only reason, however, we don't see any overall change is because as, let's call it, the dissolving reaction is a forward reaction, particles here that were actually dissolved are coming out at exactly the same rate. Because the rates are equal, macroscopically, things are not changing. So that's what we mean by a system of dynamic equilibrium. Basically, all systems would tend towards equilibrium because they're the lowest energy state. We'll see that a little bit later. It doesn't matter whether we start off with reactants or products. So, for example, I can start off with just pure powder. Okay, no water, nothing broken up yet. As I add water to it, the particles are then going to break up. They're going to then dissolve and then become kind of dissolved into solution. They're going to eventually hit saturation. They're going to eventually hit equilibrium. Or if I, let's say, mix two solutions together, I ended up having way too many particles, nothing has crashed out, nothing has precipitated yet. That's starting from all the products. Basically, what would happen is they would then collide together over time. They crystallize out to become a precipitate until they also had this forward rate equals reverse rate here. I think of it as a hockey game. At the end of the day, your hockey game will always have the same number of players on the ice, but it doesn't matter if all the players were benched at the beginning or all the players were on the ice at the beginning. We can eventually settle into the same equilibrium. The important thing is we will have a new equilibrium at a new temperature, which is why when we look at equilibrium constants, we do want to stay at the same temperature, or else we're talking about a totally different hockey game. Okay. So a couple other features of it being dynamic. We talked about macroscopically things are constant. It doesn't look like anything's changing, but microscopically those reactions, they continue to occur, but they continue at the same rate. This is super important here. When we talk about equilibrium, we are not saying the reactant concentration equals the product concentration. Just like in a hockey game here, even though we should have 5 skaters on the ice, doesn't necessarily mean that 5 skaters on the ice means I have 5 players on the bench. I may have some 20 players on the bench just waiting for their chance at a line change, things like that. The numbers don't have to equal each other. The reactant concentration doesn't have to equal the product concentration, and yet these guys here have to be constant in time. So if I have 5 on the ice, I better have 5 on the ice at all times. If I have 20 on the bench, I better have 20 on the bench at all times. As long as the line change, 3 come on and 3 go off, or 2 come on and 2 go off, as long as those rates are the same, overall there's no change on either side. Once I hit equilibrium, your forward and reverse rates no longer change. They now equal each other, and that's when we started looking at KEQ, KC. Okay? So there's 2 types of graphs that we can analyze here. One style of graph is a concentration versus time graph. I don't really care. Let's say I have an equilibrium between A and B. I don't really care where A starts and where B starts. But what's going to happen here is over time, if I have all A is going to start becoming B, A is going to start leveling off, B is also going to start leveling off. There's no guarantee, like we said, the concentrations don't necessarily have to equal each other. There's no guarantee that these lines have to equal. Maybe I'm at a temperature where reactants are favored, I have more A than B. Or maybe these can cross over, totally okay. The graph that has to intersect is actually if I have a graph of rate, how fast the reaction occurs against time. Based on how we have it here, A becoming B is the forward reaction. I'm going to call the forward reaction starts off at something positive. Our reverse, I had no B. No particles of reactants means I have no rate. So I have a reverse rate starts off at 0. By the time I naturally head towards equilibrium, these two have to intersect together. So the forward rate does have to equal each other, but you notice what I'm plotting is the actual speed. I'm not plotting the amount. I'm not plotting the concentration. In that situation, your concentrations are going to be constant in time. Our A is constantly still becoming B, but B is becoming A at exactly the same rate, so therefore there's no overall change. Chem 12 actually does a little bit more detail here. I'm just going to just allude to that. Some reactions go 100%, some go 0%. How do we know it's actually going to end up in equilibrium? So there's actually two features that we need to consider. Those two features here are enthalpy. Enthalpy we did a lot in chapter 5. This is the energy argument, and energy generally prefers to a minimum. If we have minimum, it means less energy, it makes us more stable. So what we're going to look at here is we're going to favor the exothermic direction. So for example, if I have the reaction A becomes B plus heat, on our potential energy graph, I start high and low. If I were the transition state, if I were the activated complex, if I had a choice either to go to reactants or to products, I prefer going to the product side. I prefer pointing towards the heat term because the product side will be less energy. Similarly, if I had an endothermic reaction, let's go C plus energy becomes D. If I were the transition state, I would prefer to point towards the heat term because that's the exothermic direction. That state there will be lower energy. So nature does tend towards liking minimum enthalpy. It'll point towards the side with the heat term. There's nothing fancy about that. It just coincidentally happens that way. That's only half the feature that we saw in chapter 5, though. And we also saw entropy also become important. Entropy was the matter of chaos, the disorder in the system here. The most chaotic thing I can look for is having the most particles in the most random phase. So looking at this order here, careful, this rate order is different from the speed thing that we did in chapter 6. Solids, basically the particles have really low energy, they're just vibrating in place. Instead, as you get to gases, I've heated the system up so much that they can actually expand through the rest of the container. Of course, gases are a lot more crazy, a lot more chaotic chows than our solid state. So I'm going to prefer the side that has more moles of gas. There are a few reactions for you to memorize. So Haber process is one of them here. Haber process was done about 100 years ago now. It takes nitrogen that's really plentiful in the air, reacts it with 3 parts hydrogen. You should be able to quote the catalyst for me there in producing 2 ammonia. When Haber did this, he did this all as gas, which is really nice for this chapter because gases will respond to pressure, volume, will respond to the Chatelet and all that. But basically what's happening here is I just look at the states. In this case here, I have N2 and H2. I have 4 moles worth of gas on the left-hand side, whereas I only have 2 moles of gas on the right-hand side. If nature had its way, if entropy had its way, where entropy, second law of thermodynamics says the randomness has to be increasing, entropy prefers the side that has more moles of the most random phase. So if those two features, I'll give you the sort of conditions here, if those two features both point in the same direction, so in this case here, our maximum entropy wants to go to the left. This one here, as written, is actually exo, so this one here is actually plus heat on the right-hand side. Our minimum enthalpy actually wants to go against each other. Whenever we have this compromise, we end up with equilibrium. Basically, the entropy argument wants to be on the reactant side. It's more messy. But the enthalpy argument, it's more stable on the other side. That's why we end up having a compromise. If I have another reaction, I don't know off the top of my head, but if I have it such a way that the other side is more chaotic and the other side is less energy, this is going to go 100%. This is going to go, in words we can say, completion. Or if I have the opposite of that, if I have maximum entropy point towards reactants and minimum enthalpy also points towards reactants, there's no reason for me to go forward. That's going to be 0%. That's going to be no reaction. So in that case there, we can actually have a prediction of which systems will actually approach equilibrium and which systems will just go 100%, 0%. So far from what we've seen, single replacement reactions typically go 100%. There's really no chance for the products in that reaction to come back the way it came. Okay. From here on out, we're just going to pretend we've done that already, and we can start poking the equilibrium. Our next concept is this idea of Le Chatelier's principle. Make sure you can state Le Chatelier's principle. Okay, so it doesn't have to be word for word, but some things you have to make sure you mention. You have to mention that we are already at equilibrium. If we're not at equilibrium yet, don't do Le Chatelier's principle. One condition of equilibrium here is we should be at a closed system. In case I produce a gas, I want to make sure those gas particles are still around. I want to make sure that my temperature is still very close by. Things that are going to happen, we just call it processes or nature. Nature is going to try. It's not actually going to get rid of it completely, but it's going to always go against you. If you cool things down, nature tries to heat it up. If you heat it up, nature tries to cool it down. It's not that nature prefers it to be a particular temperature. It just hates what we do. We poke the system and nature fights against you. Okay? So just conventionally, you can think about it as nature tries to undo what we do. We separate it between our stress. This is how we poke the equilibrium. And then we use the terminology of shifting. Equilibrium is going to respond. It's going to shift to the left to products or reactants to try to go against you. So let's look at these in a few in succession here. We'll start off with the temperature condition here. When temperature decreases, the reaction gradually shifts to produce the side that has the heat term. So let's imagine I have A plus heat, equilibrium with B. We already know from Le Chatelier that we are at equilibrium. So I don't even need to worry about the entropy, enthalpy stuff. I already have a situation where forward rate equals reverse rate. Now what I'm going to do is I'm going to come along and I'm going to heat up the entire box. When I heat up the entire box, it's true. A heats up, the heat and the B all heat up. It's just easiest to track. If you think of heat as a chemical, if I heat up the energy term, basically I'm going to prefer the side. I'm stuck in this container. I'm going to shift towards the side that doesn't have the heat term. I'm going to shift, in this case here, to products so that A can soak up some of that heat. It's going to become chemical B. Chemical B is actually going to be at a higher energy, but at least that heat here isn't heating up the rest of my box. So I heated it up maybe 10 degrees, and maybe some of the A is going to absorb some of the energy, so it brings the temperature back down maybe 8 degrees or so. I'm not going to get it back exactly to what it was beforehand, especially because I changed temperature. We're actually going to be a new equilibrium when we actually end up hitting equilibrium again. But basically what's going to happen is I'm going to shift. Language here I can say is I can shift to products, or I can use language of direction, so it shifts right. And in that case, products are then favored. Again, Chem 12 does this a little bit better here. It's going to show you all these graphs in succession. Because this heat here is slow to respond, I heated it up as my stress. It slowly responds by soaking in some of that heat. A will gradually drop. Let's say this is our A in our example. A will gradually drop and B will gradually go upwards. It'll be gradual changes in anything that I've plotted the concentrations. This is not so when we do concentration. So let's say I came along here, same equilibrium. Let's rewrite it here. A plus B becomes, A plus heat becomes B. Just keep it simple here. Let's say this time here, what I chose to do is I tried to pull down A. It's not that nature was really fond of having A. Nature just hates what I did. So what I did was I removed a bunch of chemical A. I removed the reactants. Nature is going to try to shift towards the side to try to replenish some of the A. I can make more A by causing B to shift to the left. In that case there, you'll notice my stress was applied all at once. In that case there, my curve, so A, whatever line that I was earlier, I pulled it down all of a sudden. It's going to be a sudden steep jump just in A, and gradually what's going to happen in B, B is going to, as B gets used up over time, B is going to steadily drop as A tries to come upwards. Right? So we are going to get a sudden jump, especially if it's a concentration change. It's going to shift to try to replenish some of the A. Here we see that when it comes, it's never going to get back up to where it started, but also because we're sort of linked in a mole ratio, however much A that I gain is going to be in a 1-to-1 ratio, because this was a 1-to-1. If it was 1-to-2, that would be scaled on this diagram here. The other thing that I want you to see on this graph here is yes, the starting and ending amounts are different. So A started out here and B started out here, and now A is down here and B is down here. We saw that once we got to our equilibrium constant, once we got to that Kc, Kc was a quantitative way of comparing products and reactants. By the time the shifting has occurred, because the temperature is still the same in this shift, if I took the starting, in this case here it's going to be B on top, A on bottom. If I took the starting B divided by the starting A, that's going to be the same as the new B and the new A. This ratio here actually ended up being the same. So Kc, make a note to yourself, only changes with temperature. So in this case here, although the initial and starting amounts are totally different, when I do the product over reactant ratio, it ends up being the same. That division ends up being the same. Okay. Also, what they like asking you, just in words, especially paper 1, they actually ask you, let's look at chemical A. Lots has happened. During the stress, it suddenly jumped down. During the shift, it actually comes back upwards. Usually, they'll say the language here, compared to the original equilibrium, we would still say A has decreased. Yes, A decreased when I pulled it down. Yes, A actually came upwards during the shift, but when I compare the ending position and the starting position, A is lower than the beginning, so A has overall decreased. So graphically would be the best way of analyzing that. That's a concentration shift here. Let's do a pressure shift. Pressure specifically, again, we're looking at gaseous particles here. There's going to be sudden jumps in everything. So let's go back to the Haber process again. Let's do N2, 3H2. We are already at equilibrium. That's when we start poking the system. Let's say we go from a container where we had this much room, and let's squeeze into a tiny, tiny box. Because concentration is equal to N over V, suddenly, because the volume is a lot tinier, the concentrations suddenly jump upwards. So what's going to happen roughly here, this graph, our concentrations were just minding their own business. When I suddenly, at one given instant, that's when I poked at the equilibrium, I'm going to see a sudden jump in all the gaseous chemicals. That's just during the stress. That's how I poke the system. And then what's going to happen, because I don't have that much room here, I basically preference the forward reaction over the reverse reaction. It's easier now for 4 particles to collide together than, say, 2 particles to go the other way. The reverse reaction didn't really care. In that case there, I'm going to gradually lose my reactants and gradually gain. I'm still going to get the gradual going up and going down, but at least I'm going to have a shift that suddenly jumps in all of them. So temperature, there's no sudden jumps. Concentration, there's a sudden jump whether I added that one or taken away that one. For pressure change or volume change, only for gases, there's going to be sudden jumps in everything, and that starts off based on this formula. Concentration is N over V. A catalyst, make sure you know the definition. It's a chemical that speeds up the reaction. We can mention here it lowers the EA. It provides a different mechanism that's easier to go. The delta H is the same. But in this case here, if you lower that energy barrier for the reactant side, you're also going to lower the energy barrier for the product side. They're going to increase by the same amount. So although your rates may be different, in this case here, both rates are actually faster. Just write that there. Both rates are actually faster. I'm actually going to form reactants and form products at a sped up rate, but at least there's no imbalance, there's no shifting, there's no changing thereafter. It just stays constant. So those are just some features there. Make sure you're comfortable analyzing some of these graphs here. There were some industrial reactions that we wanted to memorize. So in this case here, I mentioned the Haber process. So make sure you know this one here. Hopefully you were able to say iron is the catalyst for that one. 2 other processes here. I'm just going to list them for you. Second process is called the contact process. Contact process is a general overview of how we end up producing sulfuric acid. It's usually called the king of acids. I produce tons and tons of it every year. Contact process starts off with just sulfur. I basically oxidize it. It's going to end up becoming SO2. All of these are going to end up being equilibrium. Mainly the contact process, even though it's referring to the couple steps, mainly the contact process is this next step here. I'm going to take the SO2. I'm going to need my balancing here. O2 as a gas. The catalyst that we use is actually a vanadium catalyst, V2O5, and that ends up oxidizing it some more to become 2SO3. Sometimes they're going to give you the delta H as a separate one. They're going to call this a thermochemical equation, where you have the chemistry on the balance equation and you have the energy term outside. We know negative delta H means exo, so we know that this means plus 196. When it's in the equation, it's always going to be a plus. It's just a matter of whether the plus is on the right side, exo, or plus is on the left side. So for contact process, I would memorize the second step here. Yeah. But it is part of a longer mechanism of equations. And essentially why we care about this, when we have non-metal oxides, this is a shout out to periodicity again, when we add water to it, we're going to eventually get H2SO4s, almost like a fancy synthesis reaction. This one will produce H2SO3s. That's what we're worried about atmospherically, because a lot of our industrial gases are producing a lot of SO2s, extra pollutants. These are ending up reacting with the water in the air and actually raining down an acid rain. So mainly I would focus on that second step here, catalyzed by vanadium. And the last one that they want you to know here is the production of methanol. In this case here, those of you that did the energy chapter will recognize this is called synthesis gas. Basically, this is a mixture that's used for producing a lot of different fuels here, and you're taking carbon monoxide, which is a poisonous gas, you're reacting it with some number of hydrogens, and we're ending up producing methanol. Methanol can be a fuel that's used directly or filtered onwards to become biofuel and whatnot, and this one here is also an exothermic reaction. Whenever we deal with these industrial processes here, we want the most bang for a buck. So in this case here, Haber process is trying to create ammonia, or contact process is trying to create the H2SO4 or SO3. Synthesis gas is trying to create methanol. They can ask you, what are the preferred temperature and pressure conditions? So in that case there, you would say, well, Haber process, well, I want to be in a small container because then the particles will be shifting to the right. So in that case there, small container, small volume means I want high pressure. In the case here, because we had the heat term as exothermically written on all of these, do I want high temperature or low temperature to shift this equilibrium to the right? Hopefully you're able to say here, I want very low temperatures. As I have lower temperatures, I pull down the heat term. I'm going to shift more of the products. I'm going to favor the product formation. I'm going to get more of my product that I want to create for how much I put in. Now remember the favorite question here. Yes, you want decreased temperature. These ones here will end up shifting it to the right. And yet be careful, but not too low or rate is too slow. Right. Remember, we're running a business here. Chemically, by lowering the temperature, it pulls it to the right. As it pulls it to the right, it's supposed to be producing more product for you. But if it's too slow, you're also having another problem that is actually not creating a bunch of chemical. Right. At this point here, I'm just going to do a quick detour on liquid vapor equilibrium. This is definitely not my favorite section in this part here, but they do include it here. A liquid vapor equilibrium. Not as fancy as the equilibriums we've been talking about, like chemicals, reactants becoming products. Liquid vapor equilibrium is exactly what it sounds like here. We're going to take a pure liquid, let's say chemical A. A is right now in the liquid state. A is over here in the gaseous state. We have to be in a closed system because it has to eventually equilibrate. If this one here became gas and the gases could actually escape, it would never equilibrate. So in this case here, we have the gas just in the environment here. We're going to wait over time. The liquid is going to be rapidly evaporating. Right? Even when it's not boiling, you just might have the lucky particle having enough energy to actually jump out into solution. Basically, what's going to happen here is we're going to have an equilibrium set up between the liquid form and the gaseous form. So A as a liquid is in equilibrium with A as a gas. This one here, careful, is a physical equilibrium. This is not a chemical change. This is not one where the bonds change. Bonds break, bonds form. This one here is just, I have actually the majority actually in the liquid state, but given the odd particles that could actually speed out, these ones here end up in the gaseous state. Eventually, they're going to hit an equilibrium where forward rate equals reverse rate. The pressure that's being applied is called the vapor pressure. So vapor pressure is the pressure applied by the vapor, by the gas, okay, when it hits equilibrium. So at the beginning, maybe I had just pure liquid, it hasn't evaporated away. I need to wait till it evaporates enough, wait till I have more particles, and once I have hit this equilibrium, I just measure the amount of pressure it's pushing down on the surface. That's called the vapor pressure. And that actually in thinking of it that way, I actually have a nice hint here. In general, your vapor pressure, it's always going to be equilibrium regardless of what temperature that we're actually setting it up at. But in general, if you have more particles, if we have a situation where we end up with more gaseous molecules, the more gaseous molecules will end up pushing harder. You're going to gradually have more particles applying more vapor pressure. So then we can do this analysis here. Well, what if I compare different solutions that have different intermolecular forces? So I have intermolecular forces, I have London that are weak forces, all the way to my hydrogen bonding, H bonding, right? Essentially, I think about it in terms of which one is going to generate more particles in the container. For example, if I have London forces, if I have very few charges, that means my liquid doesn't really hold itself together very well, meaning a lot of particles have a really easy time becoming a gas. That's going to become more particles in the air. That's going to supply a higher vapor pressure. So higher vapor pressure. Compare that to the H bonding case here. When you do H bonding, while it's not impossible for your liquid to actually escape, the H bonding is so strong in holding the liquid together, you may only get the odd particle up here. Obviously, we would need to be in a closed system or else those gases would escape. But because you have less particles up here, you're going to then apply lower vapor pressure. All right, so just use that hint there. If you have more particles, in general, it's going to be higher vapor pressure. And we had this correlation here. The stronger the IMF, the lower the vapor pressure gets. Right. Some things that don't affect the vapor pressure here. So no effect from surface area of the liquid. So I might have a container like that or a container that's small like that. Well, if I just change the surface, I might have changed how much is actually exposed to the air, but it also changes the amount of liquid that could actually evaporate as well. So no effect from surface area, from the actual liquid volume, right? Or the actual gas volume, like how big of a container you use. It's more so how many gas particles manage to vaporize away. Essentially, the higher the enthalpy of vaporization, if it's harder for it to actually vaporize, the less particles you have there, so therefore you have the lower vapor pressure. So they just treat that as an aside here, as another look at a equilibrium system. Lastly, we introduced a little bit of math to this one here. We introduced that equilibrium constant, which we called Kc. So careful, you'll need to know these names here. If they ever ask you to write out the equilibrium expression, they just want you to write out, we've been calling it Kc, or in regular Chem 12, they just call it KEQ. Just for convention's sake, we just said it's products over reactants. So say I did the Haber process. If I wanted to write the Kc expression, the equilibrium constant expression, I look at the products as written. I know it's at equilibrium, but I still call the products on the right-hand side. The NH3 is a product. It's a 2 as a balance coefficient here. Those numbers do automatically go up into the powers. That was not true for the rate law. This is only true for your KEQ. N2 and H2 cubed. So that's what the KEQ expression looks like. I would always start off with that expression with the chemicals there, and that way I don't accidentally put the numbers in the wrong place. There are a couple things that we ignore though. We always ignore solids as well as pure liquids. The reason why is because they have a constant density. So for example, let's take a small object. Let's say I have 3 particles divided by 1. That would have a density of say 1. If I have 2 of these particles, well, more particles means I have more chemical. But I might have 6 particles. Because the density is unchanged though, this is now going to take up twice as much volume. You'll notice the composition is now constant. So it was a 3 in both cases. So if, for example, one of these was a solid, instead of actually scaling the number down by a number that never changes, I just absorb that solid into Kc, and therefore I can ignore it. So long story short, if it's an S, just ignore it. For the same reason, if it's just the only L in the equation, you can also ignore it. If there were more than one liquid, you have to include both. So when we did our acid-base equilibrium, if we did like Kw for water, right? We had liquid, and we had H3O plus and OH minus, aqueous, okay, 2 there. If I wanted the Kc expression, which we ended up redefining as Kw, we would go products over reactants. The product is hydronium times hydroxide. Those are aqueous, definitely include them. This is the only L in the equation, so we treat it as pure. This liquid cannot sort of molar volume and sort of mix into each other here, so we ignore this. Instead of actually going divided by water squared, that's all it's going to be, and then next chapter we called it KW. Right? So if it's the only L, you can then ignore it. KEQ is this product over reactant ratio when things have hit equilibrium. Sometimes when we're not at equilibrium yet, we need to use ice tables to sort of sort our system out, initial, change, and equilibrium. We define Q. Q is basically a Kc at any, can't spell, at any concentrations. Usually we're not at equilibrium, and usually we compare how does our Q relate to our KEQ. Some other general comments here. Because KEQ is product over reactants, if KEQ is relatively big, for a fraction here to be big, it means numerator has to be big. It means I have more products at equilibrium. I can say the terminology products are favored. There's more of them, right? What do we mean by big? Essentially, Kc bigger than 1, that means products are favored. If it's small, that means it's the opposite here. Because K actually deals with only positive numbers, K can't actually drop into the negatives, so small actually just means here when 0 is less than Kc is less than 1, in that case there, the fraction has the denominator bigger. In that case there, there's actually more reactants even though we are at equilibrium. Forward rate still equals reverse rate, but at that hockey game, we actually have more of one than the other. We ignore the units because we saw in our notes here, each of these actually have to do with the rate constants. They actually have K, and the K actually had already canceled out the units. So therefore, the Kc, the equilibrium constant, can actually have no units. So if you have a problem that sets up an ice table here, we're going to set up a row, use the chemicals as a header. Let's say, just make up an equilibrium here. Use the chemicals as a header with the balance equation with the coefficients there. Let's say I start off with just pure HI. You would write that number. Typically, we only put numbers here only as concentrations. So if they only give you, I pump in 2 moles and it's in a 5-liter container, don't put it in 2 moles. Actually, moles would work as well, but in general, it's easier for concentration because then it works really nicely with Kc. So we go 2 divided by 5, 0.40. Because the implication here is I put in HI and I didn't put in H2 and I2, they may not say, by the way, I'm not adding H2 and I2. In the wording of the question, you can just say 0 and 0. If you don't happen to know what the change is going to be, we're going to use X. The change actually happens based on the reaction. So this follows the mole ratio. So this will follow your coefficients. So this drops by a negative 2x. That goes up by x. That goes up by x. One side's going to be plus. The other side's going to be minus because there's going to relatively go just in one direction. And then we end up here x. We just crunch through the math here, 0.4 minus 2x. And now because we had made sure that these ones here are equilibrium, you can punch these directly into Kc. Remember, after you do your expression here, you're going to end up getting x equals something. Do yourself a favor and actually look back. What was the question asking for? It might have been asking, what's the equilibrium concentration for HI? I look at the equilibrium row, I look at HI, I still need to do this math. Don't just find the x there, punch it back into that formula, and then actually calculate what's 0.4 minus 2x there. So that's that change line there. Commenting in general, if it's not so clear which one's plus or minus, if my Q is currently less than Kc, you can think about that there. That's sort of like products over reactants. Right now, my ratio isn't big enough. So as I approach equilibrium, I want this ratio to go up. For my only ratio to go up, I need more products and less reactants. So when Q is less than Kc, I shift to products because I'm too small. And vice versa here, let's say my Q is actually bigger than Kc. Right now, when I test product over reactant, my fraction is too big. So what would happen then is, again, you don't need to memorize it. My fraction is too big. I want this to shrink. The only way to shrink it is to shrink the numerator and increase the reactant. So therefore, I'm going to shift to reactants, and that would then tell me which side is plus, which side is minus, especially when it's not obvious. Right? So make sure you practice a lot of questions with Kc here. Pretty much I said Kc only changes with temperature. Sometimes they try to cheat a little bit. Sometimes they actually change the reaction on you. Let's say I have A and B become C. Maybe our Kc is C over A times B like this. I'm just going to assume that they're all gases. What if I ask you, what is it C and A plus B? That's actually not changing Kc. That's sort of like asking you, well, it's a totally different equation. Well, my Kc has it now upside down. A and B are now products, and this is C. Kc is actually going to be the reciprocal of the original Kc. So basically, it takes the inverse. If you scale the equation up at all, so if I make it 2c, 2a, and 2b, basically all that would happen, you can just write it out. Let's do double prime there. A squared, B squared, and C squared. This is just going to be 1 over the regular Kc, but squared. Everything just scales up normally. If you end up adding reactions, okay, I'm not going to demonstrate this for you, but if you end up adding reactions, you just add the K1 plus K2. Because you're doing the first one, then you're adding the next one. You can verify that for yourself. Sorry, multiply. Okay. Right. So, aside from only temperature changing Kc, this is the other way they could ask you changing Kc. At the really end of this review here, again, Chem 12 does solubility as a total separate chapter. We're just going to do this as a application of the equilibrium stuff. Basically, you do need to know the definition for solubility. Solubility is what's the maximum amount that you can dissolve in a given amount of solvent. We typically just did solid into liquid. And basically, when you're in equilibrium, we can use the term saturation. That's when you have solid that's just sitting there, but the dissolving rate, the rate at which you become broken up into ions, is matched up with how much actually solidifies back out. We can call that term here solubility. The amount of moles that's needed to accomplish that depends on the chemical. You can quote it in either gram per liter or even mole per liter. If you want to convert in between, you just need molar mass for that. Right. So every chemical will have its different solubility. Obviously, if you change temperature, the Kc value is different. The solubility might change as well. Chem 12 actually differentiates between 2 different types of substances you can dissolve. One is ionic substances, which we're going to call electrolytes. Electrolytes always produce electrically conducting solutions. If you remember, for us to conduct, you need to have charges and you need to have to be mobile. If I have an ionic compound that dissociates, let's say NaCl breaks up to become Na plus and Cl minus, although in the solid state there's charges, but they're sort of stuck in place, not conductive. Now in the aqueous state, those aqueous ions can actually move around. In that case, they're definitely soluble. The more ions, the more conductive the solution is going to be. So ionic solutions, let's compare that with the covalent case. The covalent case here are typically called molecular solutions. As molecules, when you bubble them into solution, let's say I bubble methane into solution here. Methane is covalently bonded, so it doesn't break up as easily. Water can't chop up these covalent bonds. Covalent bonds are stronger, and water won't stabilize it because this is not charged. So molecular solutions here are not conductive, whereas ionic solutions are. Some other terminology here. When they use the term saturated, it basically means I've already thrown in the solubility limit. I've dissolved in the maximum amount. In grade 11, we just said, oh, it's just the amount when the first crystal then ends up appearing. In this case here, because we know equilibrium, we're actually loading it up as much as you want, but we've hit a situation where we're now in equilibrium. Dissolving equals recrystallization. So if you end up tossing more solid, that extra solid will just sit at the bottom. Right? It's not going to dissolve anymore because you passed that saturation limit. We just said forward rate equals reverse rate. For this whole chapter, we always put the solid on the left side. So let's say I have AgI as a solid. If I want to write out the equilibrium expression, Ag plus and I minus, solid on the left side. So therefore, when I try to do a Kc expression, products over reactants, it's going to be Ag plus, I minus. If there's any coefficients, I need to scale it up. But I end up dividing by a solid, which I ignore. So that's why I've just, the product concentration multiplied. Chem 12 typically calls this KSP. Doesn't really matter what the subscript is going to be, but the subscript in this case means solubility product. Once the thing is soluble, once the thing is broken up, it's the product between those two concentrations there. Right. From our pink sheet, we just arbitrarily call it soluble. If I manage to dissolve more than 0.1 moles per liter at 25 degrees, we'll refer to you as soluble. Everything dissolves to a certain extent. So things that are soluble, like NaCl, it's going to be called soluble. You toss in NaCl, dissolves. Toss in more, dissolves. Toss in more, dissolves. You eventually hit a point where you've maxed out. There's no more space for you to dissolve any more NaCl, saturated. If I throw in the AgI instead, with the AgI, it's low soluble. So you just drop in the smidgen here. You might manage to dissolve one of these particles, but it doesn't take much, and the rest of it's saturated. It's not a difference between whether I can get saturated, whether it's soluble or not. It's just a matter of how much. If something is very soluble, I need lots of your NaCl. If something is low soluble, you need very little amounts. But both situations can actually hit a saturated solution, and both of them can actually solidify out. Right? Be really careful. There's 2 main ways of actually finding these solutions here. I don't think I actually included it. So 2 ways to make a saturated solution. And it's super important depending on the way. Sometimes it follows the mole ratio, sometimes it doesn't. We're going to always assume this way here. Assume you dissolve the solid. If you dissolve the solid, you'll definitely follow the mole ratio. So let's take a solid here. Let's take PbI2. Right. So we start off with a container. There's no concentration just yet. You take PbI2 and you slowly drop it in. What's going to happen to this PbI2 is PbI2 is going to break up to become Pb2 plus and 2i minus. But it turns out PbI2 is defined as low soluble on your pink sheet. It doesn't dissolve very well. So while you may have managed to gotten the odd Pb ion and the odd I minus ion in here, it doesn't take much, and this one here will hit saturation. We're going to wait enough time for, in this case here, the dissolving reaction to then be matched up to the recrystallization, the coming out reaction, so crystallizing. When I write this in your mole ratios here, I had dissolved an X. When it breaks up, I'm going to get an X and a 2X. In this case here, we're going to follow the mole ratio because I did start off with PbI2. This is different from the second case here. Second case, what if we mix solutions together? Because the two solutions didn't start off the same, they don't actually have to be the same mole ratio. So what this means here is I may have had PbNO3 I may have had the Pb actually in one solution, and I actually had the I minus actually come from another solution, maybe it's Ki. You did this actually during your lab. You mixed two clear solutions together, and then suddenly you ended up with the same PbI2, you still ended up with saturation, you still ended up with this equilibrium, but suddenly the forward rate was equal to reverse rate. In this case here, it does not follow mole ratio. And worse yet, not only does it not follow mole ratio, I can't just go X, X, and 2X and all that. We also need to worry about a dilution. This one had a V1, this one had a V1. You need to do a C1, V1, C2, V2 for what happened to the lead, as well as a separate C1, V1, C2, V2 for what happens to the iodide. So this one not only doesn't follow the mole ratio, I actually have to do two dilutions. Right? So depending on how things are set up for you here, always assume the easier of the two, which is start off with a solid. I don't need to worry about mixing or anything. Follows the mole ratio. In a case when during our lab we had diluted down different samples of lead, different samples of iodide, when the concentrations got to be so low, we may have had numbers that are so tiny that that yellow precipitate actually couldn't come out again. Right? So careful when you're applying it to solubility. That's what you're going to be looking for. This TIP is basically the name that they use for Q here, exactly the same as we used earlier. When Q is less than KSP, there's not enough ions, so there's no precipitate. Basically, your any solid will end up dissolving. Your products are favored. You can verify that. Products are favored. If you're TIP, this becomes a limit. If you're anything beyond the TIP, beyond the saturation limit, now we have way too many. Our reactants are favored. Our reactants are going to be the solid. So we have way too many ions in solution. They crash out of solution. So in this case here, a precipitate definitely forms. This is just finishing up a little bit of Chem 12 stuff here. They apply it to what's called the chloride titration. Turns out silver and chloride end up doing a precipitate. You use chromate as an indicator, which ends up forming a compound that's red. Basically, you drop in a solution. Maybe I have a solution that has some unknown amount of chloride in it. You're going to drop in the silver, maybe from AgNO3. As you drop in Ag into it, Ag is going to gradually kill the Cl-. You would have already had chromate indicator inside. Once all the chloride is completely gone, the silver complexes with chromate and ends up showing a red color. So when the red first appears, we know to stop our titration. We know to take down our volume readings at that point there. Right? So that's a titration. Water hardness. We don't have much of a problem over in the west coast here, but if you go over into the prairies, you might find that the water is actually, it tastes funny, and also it doesn't lather soap very well. That's because there's the presence of other ions, these heavy metals in water. So what we end up having to do is we end up trying to do something called the common ion effect to change the solubility. So this is what we'll end off with here. If I have a solid AX becoming A plus and X minus, the question here is how can I increase the solubility? If I have all this hard water, I have all these ions, I don't want all these ions in solution, I want to crystallize them out. It's basically back to Le Chatelier. You can increase the solubility, you can make more dissolve. That just implies that you shift right. So what can you do to shift right? Unfortunately, I can't take a pair of tweezers and grab these ions out, But what I can do is I can add, let's say, a chemical N. If A and N end up solidifying out, that's going to end up pulling down the A+ concentration. As I pull it down, the Liciatelli guarantees me more of it's going to dissolve. More of the powder dissolved, it's going to be more soluble. Or vice versa, a common ion effect. I add something that has already an ion inside. What if I add like M and X? Now, I don't really care about the M part. That gives me M plus and X minus, but that ends up increasing the X minus. As it increases the X minus, I end up shifting over to the left side. That would then decrease the solubility by adding something that's in common. The one that's super tempting, and I'll end off with this here, you cannot add any more AX. At first, you might be like, oh, adding more powder, obviously shift right because I want to get rid of it. Because solid has a constant composition, adding AX has no, does not shift. There is no shifting of the equilibrium because that number didn't change. Okay, so in a nutshell, that's equilibrium, and then we applied it to solubility. If you have any questions, just let us know. Thanks.